You
Good afternoon, everyone. Welcome to the third OEH seminar for this semester. Today we have Dr. Yu Hao Liu with us. Graduated from the Faculty of Forestry, Dr. Liu has been working primarily on vegetation monitoring for cities using time series for satellite images. He has developed a strong interest in Earth observation, cartography, and graphic design. Dr. Liu enjoys making sense of things, especially and trying to make it artistic at the same time. Today, Dr. Liu is going to introduce the basic science behind Earth observation and his most recent research project. More importantly, he would like to spark conversations among students and the faculty members at SPPH in terms of how he can use his knowledge and skill sets in the field of public health. So please welcome Dr. Liu.
Thank you everyone for coming. My name is Yu Hao, or you can call me Bean, Coffee Bean. So today I'm going to, so there's 3 stages of my talk. So first, I'll introduce some basics about remote sensing and GIS. Does anyone graduated from geography? Yeah. Geography? Oh. And do you guys know anything about remote sensing, GIS? Have you heard of it?
Yeah.
Used it before?
2 months.
Okay. If I make mistakes, don't email me afterwards. So the talk I'm going to give today is people and pixels, and I think it's the best way to summarize my PhD work and also my personal interest. So something about me: I graduated from the Faculty of Forestry. I was working with the Department of Forest Resource Management, but I did not work on the conventional way of forestry. So I did not go to field trips. I did not cut down trees. I don't know anything about fish and wildlife. Instead, I was sitting in front of my computer and looking at satellite images. And that leads to my my grad school. So I did my PhD with Integrated Remote Sensing Studio at UBC as well. So focus on the urban part of the, I guess, urban forestry-ish. So, people and pixels. What do we know about people? There's a new term called anthromes, or so this concept of us disturbing nature has become very, I guess, popular these days. Climate change, deforestation, and just massive scales of the thing called human footprint. So this is us. This is Dubai. I believe this is from 1995 to 2005, so just 10 years. So our impact on the nature ecosystem is so massive that you can see it from space. So this is a typical example of remote sensing. And remote sensing is how we measure human footprint. It is not a model, it's a direct measurement of our impact. So, anyone know what a pixel is? What is a pixel? You guess? Have you heard that term before? Yes, that's the smallest unit you can see. So if you have a photo with you, you can keep zooming in, and once you see the little square, it's usually come in squares, so that is the pixel. So pixel is actually a made-up word. It stands for a picture element, so that is the smallest unit on the image, and it measures how much energy got reflected from the surface. For example, can I borrow this? So this, you can see it's orange. Sorry if you're colorblind. So that is orange. So why this is orange? Because the pigment inside this paper, it observes every wavelength but orange. So it reflects orange. And fun fact, the least favorite color of a tree is green. Trees reflect green. It hates green. It loves red and blue. Oh, this is fancy. So that's why all the trees are green, because tree hates green. It's very ironic. So here is, like I said, if you keep zooming in on the image, so this is what I used to oh, hello? This is fun. So this is most of my PhD looks like every day. Just keep zooming in the images. So again, pixels are very fundamental in this study of remote sensing, which is the detecting and monitoring process of the physical characteristics. Like I said, it's not a model. You're not building a model. You're actually measuring the energy reflected from the surface. And again, that energy can be detected from a satellite, or a plane, or a drone, or even your cell phone. And in fact, the reason why you can see me right now is because I'm releasing energy and your eyes can detect me. So you are remotely sensing me. We don't have any physical contact. So that's the very definition of remote sensing. So there are two very important elements of remote sensing, and also the universe is space and time. So often we're dealing with space, also known as resolution or scale. So resolution here, I mean the spatial resolution, which is the size of the pixel. So the bigger the pixel, the finer the image. Sorry, the bigger the pixel, the coarser the image. So if you want a very detailed view of the Earth, you want a very, very, very small pixel that you can see how many cookies I have on the plate. And time, also known as a frequency or revisiting time. So when people say, okay, this satellite has a frequency of 1 year, that means it takes an entire year for that satellite to come back to revisit the same spot. Any questions so far? And by the way, if you have any questions, you can stop me and I will answer your questions. And most importantly, those two elements are not separate. They're always interacting with each other, and we have to make trade-offs. So time, frequency, and here is how. So this video is a satellite system called Landsat. It is the longest Earth observation program so far. It has been imaging the Earth since the 1960s, 70s, and they're still operating right now. So here's just a short introduction of Landsat in terms of time.
As a Landsat satellite flies over the surface of the Earth, the instruments aboard the satellite are able to view a swath 185 kilometers wide and collect images along that swath as the satellite proceeds through its orbit. The spacecraft travels at approximately 4.7 miles per second. The satellite travels from north to south while it's over the sunlit portion of the Earth and travels south to north over the dark side.
So I just want you to pay attention to the time here. So that will tell you how frequent Landsat is in terms of revisiting time.
One orbit takes about 90 minutes. So that's about approximately 15 orbits in the 24 hours. The orbit's maintained such that after 16 days, the entire surface of the Earth has come within view of the Landsat instruments while sunlit. And then on day 17, the first ground path is repeated, so we get to view the entire surface once every 60 days.
it still gave me goosebumps. So Landsat is the reason why I'm able to finish my PhD. So I've been using images from Landsat all the way back from 1984 until 2014 for 25 cities around the world. So that's a very valuable data set. And most importantly, it's free. So if you'd like to get your hands on the Landsat imaging, feel free to email me or to come visit me upstairs. I can show you how to get those images. It used to be $400 per image. So now it's all free. But what's the second element of remote sensing? So that's time. What's the second one? Space. So space is also known as scales or resolution. So when you see, so every map has a scale. So for example, you see 1 to 10,000. So that means 1 centimeter on the map represents 10,000 centimeters in real world. So that's the second element of remote sensing. And I found a really old video made by IBM. It's called Powers of 10. So have you watched it before? Okay. You're not that old.
No, we shouldn't find.
Okay. So it's very interesting. It talks about the importance of scale, and I think everyone that involves in the science of geography or remote sensing should know the concept of scale. Okay.
The picnic near the lakeside in Chicago was the start of a lazy afternoon, early one October. We begin with a scene 1 meter wide, which we view from just 1 meter away. Now every 10 seconds we will look from 10 times farther away, and our field of view will be 10 times wider. This square is 10 meters wide, and in 10 seconds the next square will be 10 times as wide. Our picture will center on the picnickers, even after they've been lost to sight. 100 meters wide. The distance a man can run in 10 seconds. Cars crowd the highway. Powerboats lie at their docks. The colorful bleachers are Soldiers Field. This square is 1 kilometer wide, 1,000 meters. The distance a racing car can travel in 10 seconds. We see the great city on the lake shore. 10 to the 4th meters, 10 kilometers. The distance a supersonic airplane can travel in 10 seconds. We see first the rounded end of Lake Michigan, then the whole Great Lake, 10 to the 5th meters. The distance an orbiting satellite covers in 10 seconds. Long parades of clouds. The day's weather in the Middle West. 10 to the 6th, a 1 with 6 zeros, 1,000,000 meters. Soon the Earth will show as a solid sphere. We are able to see the whole Earth now, just over a minute on the journey. The Earth diminishes into the distance, but those background stars are so much farther away, they do not yet appear to move. A line extends at the true speed of light. In 1 second, it half crosses the tilted orbit of the moon. Now we mark a small part of the path in which the Earth moves about the Sun. Now the orbital paths of the neighbor planets, Venus and Mars, then Mercury. Entering our field of view is the glowing center of our solar system, the Sun, followed by the massive outer planets, swinging wide in their big orbits. That our orbit belongs to Pluto. A fringe of a myriad comets too faint to see completes the solar system. Ten to the 14th. As the solar system shrinks to one bright point in the distance, our sun is plainly now only one among the stars. Looking back from here, we note 4 southern constellations, still much as they appear from the far side of the Earth.
This square is 10 to the 16th meters, 1 light year, not yet out to the next star. Our last 10-second step took us 10 light years further. The next will be 100. Our perspective changes so much in each step now that even the background stars will appear to converge. At last we pass the bright star Arcturus, and some stars of the different. Normal but quite unfamiliar stars and clouds of gas surround us as we traverse the Milky Way galaxy. Giant steps carry us into the outskirts of the galaxy. And as we pull away, we begin to see the great flat spiral facing us. The time and path we chose to leave Chicago has brought us out of the galaxy along a course nearly perpendicular to its disk. The two little satellite galaxies of our own are the clouds of Magellan, 10 to the 22nd power, a million light years. Groups of galaxies bring a new level of structure to the scene. Glowing points are no longer single stars, but whole galaxies of stars, seen as one. We pass the big Virgo cluster of galaxies among many others, 100 million light years out. As we approach the limit of our vision, we pause to start back home. This lonely scene, the galaxies like dust, is what most of space looks like. This emptiness is normal. The richness of our own neighborhood is the exception. The trip back to the picnic on the lakefront will be a sped-up version, reducing the distance to the Earth's surface by 1 power of 10 every 2 seconds. In each 2 seconds, we will appear to cover 90% of the remaining distance back to Earth. Notice the alternation between great activity and relative inactivity. The rhythm that will continue all the way into our next goal, a proton in the nucleus of a carbon atom beneath the skin on the hand of a sleeping man at the picnic. Ten to the 9th meters, 10 to the 8th, 7, 6, 5, 4, 3, 2, 1. We are back at our starting point. We slow up at 1 meter, 10 to the 0.
Okay, they're gonna zoom into his hand, so I'm gonna skip that one. So that's what happened in the micro level. Yeah, it's not relevant to what I'm doing. Okay, so that's an overview or a fun way to introduce the concept of scales or resolution, if that's appropriate to say. Where's my pen? So right now, I would like you to have a paper and pen. Thank you. So we can reinforce the concept. So on the Y, we have the space, and then on the X we have time. So there's actually a third element in remote sensing, or the element that we have to care about is money, the cost. So logically, the finer the image, the more expensive to collect. So I would like you to give me some examples of some events. I can start. How about wildfire? Yeah, so just all the nasty smokes. Do you have any other examples? Typhoon? Well, okay. What is the typhoon?
Certification.
Okay. Remember that video I showed? Certification. So those are very, it happens at a larger scale. It's continental, or in that sense, it's not just a city block. Do you have any examples that happen around neighborhoods that the public health cares about? Well, I guess they care about.
Densification. What's that?
Sorry?
Measles outbreak?
Measles.
Well, there was a guy with measles on one of the ferries.
Okay.
I don't know. Like, sorry, maybe I didn't understand the question.
So anything that, okay, what else? Like, for example, a park. So City of Vancouver decided to put in a new park in the city. New park. Traffic. Thank you. Terrible stuff. Any one more? Enforcement? What do you mean enforcement?
Urban forestry.
Urban forestry. Can you be more?
Forest in the city. Trees in the city.
Okay. Trees in our cities. Okay. So now let's put those events onto that figure. So wildfire. Do we need a very fine image for fire? Not really. So along here, maybe here, somewhere in here. And how frequent do we need to collect images? Daily?
Depends on, well, it depends on what it is that you are
Right.
trying to understand.
Okay, let's say we want to study how forests recover from the fire.
And not very.
Okay, so maybe around here. Typhoon. So that's a weather map. So not very fine. How frequent?
Very difficult.
So here. So I think justification, not very fine, and it happens really slow, right? So maybe around, and then this, I think it's at larger scale than fire. So we can put here. Okay. Parks. Parks has to be around here, right? And how frequent? How often we put in new parks? Not every day. Maybe once every year, every couple of years.
Yeah.
So let's say, but not as, but as be more frequent than fire.
Yeah.
It depends, I guess. So around here, park. Traffic.
Fine.
Very fine. Both time-wise and space-wise. So we want to be here. And trees in our cities. What do you mean trees in our cities? What do you want? What information do you want?
Density, trees.
Okay. Like you want to detect the health of the city, or the trees, or you want to count how many trees?
Yes, say where trees are more localized, to see the distribution of trees in the city.
Okay. So we're talking about at least the tree level, sea level, so very fine. Maybe not as fine as traffic,
Focus line of traffic,
and then not as frequent as,
not as frequent as parks.
so let's put it here. Yeah. Trees. How often do you see hourly updated traffic satellite images? Doesn't really happen because of these. It's too expensive. So the reason why I put these figures in here is I noticed, well, this is my third week in public health. So I noticed, at least in our lab, the research we do is very fine scale. So we are looking at very detailed images. So we are looking at anything above here. And depending on the events we want to study, what's the typical public health event?
Hospitalization,
Okay. So what do you mean? How?
people being admitted to the hospital for various reasons related to one of these
Right.
factors.
Okay. So for example, we can study the distribution of hospitals. So that we don't need hourly. We don't do hospitals every hour. So maybe we're looking at somewhere in here. Okay, so just draw a square for SDPH. So that's my understanding of what level of details we need for the research we do. And of course, as we move towards that corner, the cost is going to increase. It's very expensive to get images. It's not just the cost to get images, also the cost to hire people to analyze the images. So I think you guys have a good understanding of remote sensing. Do you have any questions so far? Do you understand the interactions, the trade-offs we have to make between resolution and time? And cool. I think you guys are smart enough to understand my PhD. So this is my PhD. So I did green space versus socioeconomics in the region of the Pan-Pacific or the Pacific Rim. So this is a map of all the cities with 100,000 residents. So my study area is, like I said, it's the rim. And this is a very important region in terms of urbanization because lots of us live in those regions and it has the most populous densely populated cities in the world. So traditionally, how people are still using data like this. Do you know what it is? It's census data. Very old census data from the 1870s. So it has its position in terms of studying urban. It's very well documented for most of at least for some part of the world. So this is what we used to get our information from in terms of urbanization, so demographics, people's income, and now we can also study their health. But the gap between these and this is the space. So we know all the information, but we need to know where they are. So my research first uses the images captured from the daytime from Landsat from 1984 to 2012. So I have images of my cities every single year, and I can generate an index that represents how green that city is. But again, looking at that figure, I cannot afford to have daily images because it's very expensive. And I know, fine detailed images. And usually fine detailed images are not updated as frequent as, well, I guess you can, but again, it's very expensive. So I use annual images, and because trees grow not that fast, so I think it's well justified. And also, very interesting, there's also images from the nighttime lights. How many of you have heard of nighttime lights images? Hey. So it is known to be a good proxy to wealth. The assumption is a brighter city is a wealthy city. They can afford to light the city up. And I have the images from 1992 to 2012, and there is a gap is because that sensor is relatively new compared to Landsat, because Landsat is the longest Earth observation program. And this is, you can just focus on the graphics. So this, do you know what city is it? Anyone? So which city has more grain in the center than, so usually when people think about cities, it's greener in the suburbs, right? When you move away from the city, it's getting greener and greener. So why this one is green inside the city, but not that green outside?
Was it in the desert?
Yes. That's Vegas. So that's Las Vegas. So again, I have the annual images of Las Vegas, and I generate how green Las Vegas is, and I can generate how fast, because I have the time series, I have the trend. I can calculate how fast the city is getting greener or how fast the city is losing trees. And then because it's all spatial, we have space and time, I can tell where and when it happens. And then the same for the nighttime lights. Again, I have the time series. I can do change detections. I can know in which year which pixel got lighted up. So that's a good representation of urban sprawling. So we can know exactly how and where the city is expanding. So why am I doing this? It's because there's a theory called environmental Kuznets curve. How many of you have heard of environmental Kuznets curve? No? Oh, okay. So this theory is basically assuming that at the early stage of any economy, the environment will suffer. And then once the economy gets better and better, when city gets wealthier and wealthier, they can afford being green again. But usually those type of studies are done based on, like I said, census data or economic data. They're very tabular, just Excel sheets, not very spatial. I don't really like them. And I was trying to use remote sensing as a tool to measure those two variables. So we have the economy represented by the brightness of the city. And we also have the vegetation as indicator of the environment. So my assumption was the greener that city, the better environment it has. So what I did is I have the time series of vegetation. So I have a trend of how vegetation is changing. And I also have another trend for lights. And then I can compare, are they linearly rated or quadratic rated or cubic? So this is the environmental Kuznets curve. It goes up and then down. And because, again, in remote sensing, we have space. We can map them. So we can see which model, the distribution of the models. So those are the two examples I made. So one is for Calgary. Anyone from Calgary? Alberta? Anyone from Tokyo? No? Okay. So so these maps, so each pixel, what is a pixel?
Smallest unit.
It's picture elements, it's smallest unit. So every pixel will have a number, and that number represents which model is the best to explain the relationship between urban greenness and city brightness. So I also want to know, because I have 25 cities, I also want to know, is there any similarities or differences between different cities? So the typical, so these are 3 cities, Shanghai, Melbourne, and Vancouver. Anyone from Shanghai? Melbourne? No? Okay. So I noticed that for developing cities, they kind of follow the same trend, but takes less time for them to reach the same level of urbanization. So in other words, they're faster in terms of urban sprawling and densification. So with all the information I have, and then I can map out how connected those cities are in terms of their spatial and temporal changes. So there's a few interesting links. So we can find that Shanghai and Tokyo, they're highly similar in terms of their greenness and city brightness changes through time. And also Singapore and Bangkok, and Denver and Phoenix. I think there's another one in Australia. No? Yeah, they're Tianjin and Manila. So the way I did this is I did a cluster analysis. So basically I'll ask computer, find the most similar cities, and I use 4 different variables to do the analysis. So if the cities are in the same group every time around the cluster, that means they're highly similar because no matter which variable I use, they always end up in the same. So these lines basically tells us the chances of the cities being assigned to the same group. So if it's 100%, that means they're highly similar in terms of their spatial and temporal changes. There are the 3 key lessons I learned, and I wish I could go back and fix them, is city selections. How do we select cities? So in most researches here, our study areas were assigned or given by our clients or by a supervisor. For example, in our lab, we study Metro Vancouver. So we don't have to worry about, which city we should include, which city we should exclude. But in my research, because I have potentially the images for the entire Earth. So the first, the struggle I have is which city I should include and how can I select cities to represent the whole spectrum of urban environments. And the second is where do you define city? How do you define a city? So have you guys driven on highway and it says Vancouver 23 kilometers away? What does 23 kilometer mean? If you keep driving 23 kilometers, do you reach the boundary of Vancouver or are you ended up in the center of the city? So, and again, I have the images of the entire Earth. So I need to figure out a way to define my city. Do I use census boundaries or I use a circular buffer boundaries? And the last one is the environmental goodness curve is a very popular concept among social scientists and economics. And remote sensing data only been used, I think, twice. The second one. It's not really applied in other disciplines, such as the School of Population and Public Health. So, yeah, and right now I would like you to, we can just chat about ideas and for my future research. I'm no longer with people anymore. I'm with Public Health, Public Health and Pixels. Any, if you have questions or research interest, just let me know. Yeah.
So thank you very much for this. I guess the room is open to questions, interests.
My question is, can you use the data, what you found, to kind of model predictions
In terms of
of like the breeding or breeding species
Yes.
in cities
Yeah.
in the next 10, 20 years?
Of course, because I have data for the past 25 years, but remember, we have to go back here again. So my PhD is around here. Annual, not very, my PhD is here. So what you're asking is in here, I guess. I mean, we can,
What will happen in
but it's not going to be at block level. This Landsat is 30 meters, so one single pixel is 30 meters on the ground. I mean, we can predict the general trend in terms of where a city is doing vegetation, but that event has to be large enough, at least larger than 30 meters, to be captured by the sensor.
Coming to you, Sarah.
Thanks for this. It's very intersecting with my own interests. I guess as someone who's worked in public health for a very long time and sees huge potential in remote sensing data, my biggest concern is around training and data science. And these aren't easy data to deal with. You're really looking at an intersection between computer science and public health. I'm curious about your thoughts on how we approach that field of public health.
I wouldn't call myself a computer scientist, but I can still do remote sensing. The field is very well developed, and there's a massive online support, and the images are usually pre-processed. So my supervisor, my previous supervisor, when he was doing his PhD, his image was shipped, was mailed to his lab on the plastic paper, it's like a film. And in fact, the first Landsat, they actually dropped the film from space and then landed on Earth. I think that's 60s. So I've seen the original Landsat image that was on the film. So right now, we can download it in 5 minutes from our laptop, and it's all pre-processed and it's ready to use. And I don't see why we not. I mean, in terms of data science, it's only the spatial part is new, because you can visualize every pixel as a row in your table, and you're basically dealing with what you're comfortable with. So, is it a good question?
I'm going to have to agree to disagree on this.
Okay. Yeah, and again, it depends on the level of details. It's always a trade-off in remote sensing. Everyone wants here, but nobody has this. So.
Thank you. That's a wonderful presentation. I'm just wondering if remote sensing in public health can be useful to capture less tangible data, like pollution. How do you take images of smoke or things that are not tangible? Are we able to do that?
Okay, I don't think we can directly measure smoke. I mean, the smoke from a wildfire is, we can measure them, but I'm assuming you're talking about smoke in the city.
Yeah, it's pollution.
Pollution.
Yes.
Yeah, so as far as I know, right now, the air pollution was from local weather stations. They have, yeah. I'm not aware of any platform, but anything is possible.
Email me if you want to find out more about that.
Sarah.
Or me.
Oh, Sarah.
My question is, Lancet was your only source of data. Are there other techniques in terms of cost, like using LiDAR, that would be another?
Yes. Yeah, I believe City of Vancouver has LiDAR data and it's free. But again, we're talking about the trade-off again. So LiDAR is very detailed, but it's good for vertical structure. It doesn't have any, at least the one I saw doesn't have any spectral information. So what you get is basically the physical 3D model of the city. I mean, it's really good. You can measure, for example, canopy covers. And a friend of mine, Rory took, he did a solar study with UBC. So basically he used LiDAR and he can measure the height of the building, the aspect of the roof, and then the nearby canopies. And he made a map that shows the potential solar energies all the roofs can get inside Vancouver.
And in terms of cost, which one do you think is more costly?
Well, you're talking about free versus hiring a pilot and fly over a city.
Okay.
So, but like I said, it's a trade-off. It depends on what information you want to get. And LiDAR, it's not just useful for city planners. Usually in forestry, for example, LiDAR is it's purchased through different companies. They share data. For example, operations, they need LiDAR to make roads. So you're not just the only user. So you can have different split the cost.
In terms of precision, how small is the pixels would be?
I think the smallest one I've worked with is less than 1 meter. Yeah, so LiDAR is very accurate vertically, also horizontally.
I have a question for you. About that network analysis that you've done, right? So where you were showing cities throughout
Yes.
the world or through your city area of
Yes.
interest.
Yeah.
You found some high correlations between cities that you would not expect. So Manila was highly correlated with Tianjin, I suppose?
Yeah.
Yeah. So, so you find this, right? It's one of your findings of your doctoral work. Where do you go? What do you do with this type of information? So you find that the way that these cities evolve in terms of socioeconomic status, in relationship to their urban geography, very similar. So what do you take from this?
So how can people use this as a, so before answering your questions, there's another reason why remote sensing is really good for the study of public health. It allows us to compare cities from different places. So if we only have census data, it's very challenging for us to compare a city from Asia versus a city in North America because they have complete different census systems. They collect data in different ways. So through remote sensing, it's basically, we call them census from heaven. Every city is the same. You just collect energies from the ground. So to answer your question, I would say one of the goals, my ambition, is I gave a talk as a 3-minute thesis to UBC. So one of my ambition is to what I call let cities learn from each other. So if we have cities that share the same path, maybe one is going a bit faster than the other one. So the one behind it, can learn from their peers, I guess. So we avoid making the same mistake again. I think that's the value of having cities from different places and through time.
Can I ask you another question related to this? So can we also use that as a way to think about what not to do in terms of development, right? So basically, you showed that curve that had that quadratic form, which shows that comes a point where you start being harmful to your population if you develop too much.
Right.
So is this something that can be translated to public health? Because right now what we've done is like you look at the greenness, the past, and you look at how the greenness evolves with like how much the city is making more money. Can this be translated to health data if you had health data, population level health
Of course. I mean, the data I'm working right now, I wish I had them during my PhD. Yeah, and again, so back to this figure. So my research is in here, right? And if you remember the goodness curve, it goes like this. It doesn't really tell me which this figure is sitting on the graph. So really, even if I observe a linear trend, maybe my PhD only looking at this part. You know, because the data I have. So it's maybe the true relationship between the greenness and nighttime lights follows that theory. But because I only have data from 1984 to 2012, I'm not able to observe past that point. So that's one of the I guess the concerns during my exam. So people are asking me, how do you explain a linear trend versus a cubic trend? So everything goes back to that figure. It's the interplay between the time and space.
Okay, well, thank you very much. Oh, there's one.
It's not a good question.
There's no there. There is.
Yeah, no bad question. For a wonderful presentation. I also struggle a lot with defining what an urban area is, and I understand that there are a lot of sort of philosophical and value judgments underpinning what urban means, but given that there are different development trajectories in different parts of the world, what are your thoughts on identifying urban areas using remote sensing? What kind of approaches would you take? Just given that I think some place can be urban, but for example, have less nighttime light if it has lower socioeconomic status.
Right. Okay. So it's for me, like I said, I have an image of the entire Earth. And actually, I made a map. I processed the nighttime lights for the entire globe for the past 6 years. So my approach of that is avoiding defining city. I just get everything, and whatever boundary you have, you can just cookie cut stuff from my master map, I guess. So as for what's your second one?
Well, it was just that because urban means so many things. I guess really it depends on your research question and what type of urban environment you want to address. But it's really difficult sort of in the boundary areas, especially metro areas where you have bedroom communities that
Yes.
are developed and there are people moving into a city during the day and back out to a less urbanized environment at night.
Yeah.
Hard to define, but I feel like there are some opportunities based on a few different remote sensing derived metrics like greenness and nighttime light, maybe combined with road networks. It's not something that I have bothered doing because I've just taken sort of fairly broad census definitions, but I think it's a potentially interesting question.
It's good challenge.
Yeah. So I mean, it's not a question I can answer right now, but I'm just interested in your views.
So in the end, I decided to use circular buffer to define the city. I used 60 kilometer radius. So that's what people have been using. The reason why I ditched the census, first reason is I don't correlate my remote sensing metrics with census information, so it doesn't really matter where my boundary is. And also, I noticed because when the city developed, they don't really know where the boundary is. So often we will see a big city, and we can see there's satellite cities around it. So they have corridors. connecting highways and new small city centers. But if the census boundary is like that, and we use that as our definition of urban, very likely we'll miss that corridor, we'll miss that connection, which is very important for urban. The first reason is there are not many things going on in the center. It's likely very saturated in terms of urban activities. So most of the urban development is happening outside of the city. They're expanding. So that's the reason I want to use circular buffer, so we can capture more activities around the city. But then that brings us more questions. What happened to a city in the coast? It can't really, the city can't grow in the sea. Well, in Dubai they can, but not in Vancouver. So what happened to a city that in a valley? It can only go a linear way, only stretch like that. So yeah. So I guess I had more questions than answers after.
And I think that's a very, very healthy way to finish your doctorate and move on to more research. So please join me in thanking Dr. Liu today for his presentation. Feel free to approach him with more questions and possible collaborations in the future. Thank you.
So my office is just across your OEH student room. Activity room. So yeah, so if you're interested, if you want, try some Zelda images, I'm very happy to help you.